On behalf of the Department of Geology, Geography, and Environmental Studies, officially welcome everybody to the first seminar of the spring semester in 2021. And I'm very excited about the lineup that we have for today's seminar. We're going to be digging into a research topic with a research team of 3 people talking to us. The title today is Mid-Ocean Ridge Tectonics. The speakers that we have today are Dr. Renee Sparks, Mr. Simon Detmer, and Mr. Adam Tjoelker. And the way we'll do these introductions is that I will introduce Professor Sparks, and then Professor Sparks will be introducing the rest of the research team at whatever moments you've identified as appropriate. And we expect that we'll have time for questions as well. And the research team will kind of moderate when they want to take questions. So I don't know whether that's going to be at different times within the seminar or whether more of the questions will wait until the end. So it gives me great pleasure to introduce Professor Sparks. And as I was just reviewing, that Professor Sparks came to our department as a geologist in 2015. And in some ways, those years have gone so fast since that time. And in other ways, it seems like Professor Sparks has just always been an integral part of our department. She came to us with a PhD in geology from the University of Kansas. And then most recently, before she has joined our department here, she spent a number of years, more than a decade, at Northwest Missouri State University. And so has the benefit of a couple of different educational systems to draw from. She has certainly added to the geology that we're doing in the department, both with her work with the Dice Mineralogical Museum. And if some of the audience hasn't gone to see that museum yet, you certainly should check that out during the open hours. And she's also added to our department in terms of the research projects that he's bringing in. And in this case, we've got a research team who's been working on a very interesting direction. And so I will pass things over to you, Professor Sparks, to introduce the topic and the rest of your team. Thank you very much.
Thank you, Professor Van Dyke. We are so excited to be here today and to be able to share the research that we've been working on almost for about 9 months or so now. And so I've got 2 amazing researchers that I've been able to work with, Simon Detmer and Adam Tjoelker. And with that, this project started out as an honors project for Simon. And he was in Tectonics last spring. And we were starting to look at, well, what are maybe some tectonics that are occurring on the surface of Mars, and trying to understand that a little bit, which of course with the landing of Perseverance in the last week or so is pretty exciting. And it eventually morphed into what's going on with the polar flattening and the equatorial bulge, and maybe how is that related to tectonics, knowing that Mars rotates about similar to what Earth does. And that's kind of where things started. And then it just has blossomed into this study of mid-ocean ridges that I'm excited for us to share with you today. And then Adam joined us in January as part of the team, and really brought to the table a great understanding of mechanical engineering, how materials would behave, and then the specialty of GIS and being able to take the loads of data that we have available to us and putting those into a visual understanding and the pieces that we need to really evaluate. So with that, I'm going to let Simon get us started, and then we'll transition to Adam, and then I'll wrap things up. We'll take questions at the end of that. So Simon, I'll let you take it away.
Would you mind giving me the permission to share my screen?
Yeah, sorry, Simon, I just did that for you, and I'm working on that for your co-presenters as well.
Thank you. Can everyone see my screen? Sounds good. Thank you, Professor Professor Sparks, for a wonderful introduction. Today, I will be starting off by talking about the fundamentals of our research based on mid-oceanic ridge tectonics. On this intro slide here, you can see this photo of a ridge system, which is characterized by the red mountains that are offset by transform faulting that has occurred in the past. The fundamental goals of this project were to characterize the relationship between mid-oceanic ridge tectonics and latitudinally variations in gravity, and to determine the effect of the Coriolis force on magma movement near diverging margins. Professor Sparks will talk about that a little later today. We had two main results from our project. We found that the ridge and transform fault azimuths display marked directionality, and that variations in the lithostatic load are consistent with an induced pressure gradient between poles and the equator. To further understand the basic fundamentals of these concepts, here is an image of the major tectonic plates that make up Earth's crust. And here is an image of some of the processes that occur between the tectonic plates. In particular, we're interested in looking at what's going on at the diverging margins, as indicated circled here. Magma rises from the Asthenosphere through the Lithosphere and crust to expel it at these margins. Another faulting pattern that also occurs there is transform faulting, where two regions will slide in opposite directions parallel to each other, offsetting the ridge system. Let's now take a closer look at a cross-section of the diverging margins. Here you can see the Asthenosphere, which is the top of the mantle, and the lithosphere and the crust, which float on top of the Asthenosphere. As current literature shows, there is a melting regime that is triangular in shape down to about 60 kilometers below the Earth's surface that allows magma to rise up through the crust at these diverging margins. These diverging margins will also spread apart as each tectonic plate located here will move towards and beneath a converging margin zone. The first part of our data analysis was using GEBCO, which has the largest open source image, highest resolution elevation images of the mid-oceanic ridge systems known to the public. We then used gplate, a tectonic software, to analyze these systems. We spent part of the summer collecting data, meaning the longitude, the latitude, and the depth of several points along these ridge systems, which was not previously, or as we know it, previously documented in such a large manner. We documented the ridge systems by taking the points of latitude and longitude and depth at the junctures between the ridge and transform boundaries where the greatest depth within these systems are located. This is because the brittle zones are the weakest and therefore will be the smallest. To further understand these systems, we focus into several ridge systems, one which is the MAR, or the Mid-Atlantic ridge systems, found located from the Iceland all the way down to near the Antarctic. We documented the azimuths of both the ridge systems and the transform systems and found a high correlation between the two. We found that in the south, the azimuth of the ridge systems were 165 degrees, and the transform azimuths were nearly perpendicular to that at 75 degrees. And in the north, we found that the azimuth was 180 degrees for most of the ridge systems, and that the transform boundaries were nearly perpendicular at 90 degrees azimuthally. To better understand the next part of the research, I've created a cartoon drawing where there's a balance between two weights above a liquid. You can see that the molecules within the liquid are evenly distributed since the masses, mass 1 and mass 2, equal each other. However, if mass 1 and mass 2 does not equal each other, mass 2 will fall below mass 1 and induce a higher pressure gradient in the area below that mass, which will induce a flow from the area under mass 1, mass 2 to mass 1. If we apply that to a global model, looking at the mantle and looking at the changing gravity, which as a result of the equatorial bulge resulting from the rotation of the Earth, has a smaller gravitational field at the surface of the equator than at the poles, we will notice an induced force of magma flow in the Asthenosphere from the poles towards the equator. Here in this chart, we have documented the average lithospheric load and gravitational acceleration in 10-degree increments. In order to calculate the lithostatic load, or the amount of weight above a certain asthenosphere location, we had to use this following formula, where g is the acceleration due to the gravity, z is the thickness of the overall material, and we then took the integral of these values, and we found that the theoretical lithostatic load does vary. However, we did not use the traditional gravitational equation, since that was actually found very slightly inconsistent with the observed gravitational loads we've measured on Earth. Instead, we used this following equation, which allowed us to adjust to the gravitational loads we find on Earth. This diagram to the left shows an example of several of the variables within our calculation. 3 of the variables include the density of the crust with which we distribute, the crust, which we took the average density of 3,200 kilograms per meter cubed of basalt, gabbro, and layered mafics. We also generalized the density of the lithosphere at 3,400 kilograms per meter cubed. However, the most variable due to the change in water depth at the Earth's surface is the load that the water column presents, and the density was calculated using water found at 4 degrees Celsius, which is consistent through much of the ocean. Presented in this graph below is a summary of all of our data for the lithostatic loads of the major diverging margins across the planet. We see a general trend of decreasing loads near the equator as opposed to the poles. However, we have 3 outliers. 2 of the outliers are primarily horizontal and travel longitudinally instead of latitudinally. And 1 outlier is the outlier furthest north, which is the Gackle Ridge. One of the outliers that travels longitudinally instead of latitudinally is the Gulf of Aden, we noticed that although it didn't have a change in gravity, a significant change in gravity latitudinally, we did notice that it did have a change of and load bearing longitudinally, as there is a decrease in pressure as longitude increase in this very small ridge system. Another outlier was the Gackel Ridge, which instead of increasing with decreasing in lithostatic load towards the equator, it actually increased. However, this may be due to other factors regarding the formation of the Gackel Ridge. This graph right here presents a summary of the data collected for the Mid-Atlantic Ridge, and it shows a general trend of decreasing lithostatic load towards the equator away from the poles. This is exactly what we would expect with the change in gravity we find throughout the surface of the Earth. And the calculated pressure differences from this system is 46 megapascals, which would potentially make it possible for an induced flow of magma from the poles to the equator to occur. Now, Adam will take some time to explain why mapping and image processing is so important to further understand this question. Thank you.
Thank you very much, Simon. As Dr. Sparks introduced me, my name is Adam Tjoelker. And for this next part of the presentation, I will be talking to you guys about the mapping work that we did in supporting our theories, our new model for magma migration at these diverging margins. So why did we choose to focus on the southern mid-Atlantic ridge? So when I joined this project over interim, we were tasked with investigating this particular region of the Mid-Atlantic ridge. And so by focusing here in the southern Mid-Atlantic ridge, we can identify a diverging margin which has a quite straight north-south trending ridge, which allows us as researchers to kind of isolate the variables that would contribute to the mechanics of these ridges and think about how our model looking at Coriolis would be affected by those forces. Because if we have the north-south orientation, we can start to see how these lateral magma migrations will affect the brittle deformation at the surface that we can detect with detailed analysis of the bathymetry. And as Simon mentioned before, we were using GEBCO data products. And GEBCO just stands for the General Bathymetric Chart of the Oceans. And their goal is to provide the general public with the most authoritative, publicly available set of bathymetry for the world's oceans. And so we were able to use this GEBCO data to analyze our area of interest from about 1.5 to 30 degrees south along the southern Mid-Atlantic ridge. And so on this next slide, I'm going to tell you guys about, so the data interpolation products were really important to understand for this research. Where we have detailed bathymetry, we know that in particular areas where there's detailed bathymetry, these are derived from sonar dragged behind ships or mounted on the bottom of ships. And in these areas, we have high resolution bathymetry, which allows us to see the details of the topography. But for the majority of this area, you can see, which is in orange here, this is all satellite derived bathymetry. And you might wonder, how do satellites measure topography and bathymetry on the ocean floor? And it's quite interesting. In fact, what satellites do with satellites, GEBCO is able to collect data about the minute variations in the average elevation of sea level. And these variations will occur due to submarine mountain ranges. So where there is more mountain mass under the water, water will shift towards these areas and cause a slight bulge, which will indicate that there is some topographic relief. And so for the majority of this area, we had lower resolution satellite derived bathymetry. And just understanding the limitations and access to bathymetry really allows us to understand that we only know about 20% of the ocean floor. 80% remains, by many estimates, to be completely unexplored. And so in an area like this, where we have a large extent from 1.5 to 30 degrees south, there's large areas that are unexplored to high resolution and a high detail. But with these areas that are of high resolution, it allows us to have a higher degree of confidence in understanding the details of the topography. But although in general, though, it is very valuable to have this satellite data because it allows us to understand some of the general features. But when you're analyzing the data, you have to understand that the mountains aren't quite as smooth as they may appear in these larger views. So here in the next slide, here's a zoomed in view to the bottom of our metadata. And we can see the areas in blue where we have multi-beam sonar. And these areas will be high resolution. And in between them, we have the red color, which indicates bathymetric sounding and interpolation between the satellite products and the sonar. So where ships will travel in a linear path, this is what's called a bathymetric sounding. And you might be able to see these faint dotted lines that cross. These are paths where a ship has sent sonar soundings to the bottom and it's gained depth values in a linear path. These multi-beam sonars in blue indicate where a multi-beam sonar has been used. And this is much more, this gives a much larger area in a sweep and allows us to see the detail in a larger area as the ship crosses along the ocean. And these are very limited. For a lot of the areas, there hasn't been much sonar, multi-beam sonar research. So we really rely on the bathymetric soundings and interpolation between those soundings and the overlaid satellite derived bathymetry that we used for that GEBCO used to produce these data products. So from our perspective as researchers, it's really important to have that understanding of how this data was collected to make sure we're using the data in a way that allows us to best understand what we're analyzing. So when we download data from GEBCO, we just get a raster which has digital number values for the elevation of the topography. And so here on the left, you can see in black and white the raster that we would have downloaded. This is the raw data. You can see the lighter colors indicate higher ridges, and the deeper colors and towards black, the darker colors indicate where there's quite a deep rift valley or an area between a transform fault where it's quite deep. And so by using raster processing, including hill shading and applying a sequential color scheme and projecting this data onto a map, as you can see on the right, it allows us to really see in much higher detail the topographic features that we're interested in analyzing. And this is quite valuable for us as researchers in trying to understand the mechanics of the brittle deformation at these diverging margins, and also be able to identify the rift valley and the ridge axis of divergence, as well as the transform faults, which indicate some of the magma migration that's going on below the surface. And so, as I mentioned, using the high detail bathymetry, you can see this area here before we looked at on the type identifier grid from GEBCO. We can see this is a high resolution area, and you can see there's much more detail in the ridges where we have the detailed bathymetry, and this allows us to have a higher degree of confidence in placing the ridge axis and also identifying the transform faults, which is really important in supporting, as Simon mentioned before, the rose diagrams mapping the azimuths of these these faults and trying to understand the mechanics of the magma migration in this model. And in addition to the ridge identifying the transform segments, we can also, in the ridge segments themselves, we can also identify volcanic features, and we can see the conical shape where we have volcanism on the ocean floor. And one of the areas of interest that we identified is called the ascension fracture zone. And so spending hours analyzing this and looking at this raster data for these margins, we started to notice some really interesting patterns. So here we have, this is Ascension Island, and this right here is the Rift Valley and diverging axis margin. And you can see here we have some very deep transform faulting. In fact, this area here has some of the lowest elevation, some of the deepest trenches in this whole area of interest. And you can see how over time we can start to unpack the geologic history of this area and see how the magma migration and the shifting of the plates at the diverging axis has caused these very fascinating patterns to emerge as we look up and down the diverging margin in the South Atlantic. And so another output we created from this GEBCO bathymetry were 40 longitudinal cross sections. So along the ridge axis, 40 locations were chosen as areas of interest to produce cross sections. And these are graphed with distance on the x-axis and the elevation relative to sea level on the y-axis. And so here I have two examples from number 7 and number 9. So here you can see number 7. This is just north of a transform fault. And you can see there is some high resolution bathymetry. And along this cross-section line, you can really see where the deepest part of the Rift Valley is. And that's another very important tool for us to identify the axis of divergence and understanding the mechanics of these margins. In addition to that, we can use these cross sections by setting the scale in order to measure the actual the faulting angles that we can detect at these areas using the bathymetry. And at number 9 here, just east of Ascension Island, you can see the Rift Valley, and you can see the axial ridges on either side of the axis. And that allows us, once again, to really start to identify in more complicated areas such as this, where the axis of divergence is actually occurring. And so finally, I'll point again to the Rose diagram. So using this very detailed bathymetry in supporting the research, we were able to find an even stronger level of correlation between the faulting azimuths in this southern part of the Mid-Atlantic ridge. Using the high detail bathymetry, we found that the north-south ridge segments had a very strong agreement to a very nearly 15 degrees off a north orientation for the direction of the divergent margin axis. And then once again, for the transform segments orthogonal to these ridge segments, we noticed also 15-degree deviation with a very strong level of agreement between the different, all of the transform segments across the margin, which indicates to us that this particular area has a very strong pattern, which allows us to investigate how our model of magma migration can produce these results in the brittle deformation at the surface. And so Dr. Sparks will now continue the presentation, and she will now tell us more about the magma migration that we were looking at for this area of interest. And now I'll pass on to Dr. Sparks.
Thank you, Adam, and thank you, Simon, too. So let me see see if I can get my screen shared. Do you all see the presentation or the river?
It is showing that you're sharing your screen right now, but I'm not seeing the presentation on the screen quite yet. Now something interesting is coming up.
Well, let me try one more time.
It was looking pretty good that second time, Renee.
Is it now?
Yep, I see something on my screen now.
Earth's rotation?
Earth's rotation, yep.
Excellent. There we go. Okay. Thank you for your patience. So I so appreciate all of the work that has gone into this project so far. And, you know, when I think about the GEBCO data that we've explored, and I think about the hundreds of papers that we've combed through to understand, it's kind of fun to boil this down to what's going on in this particular area. And so as Simon started us out and Adam mentioned as well, we've got Earth's rotation being a major player in our project, and that we've got the equatorial bulge, the polar flattening, and also Coriolis effect. So with Coriolis effect, we've got, of course, because we're in the southern hemisphere for this project, we've got currents that could be moving toward the equator, and they'll be deflected to the left or in a counterclockwise rotation, as is normal for the Coriolis effect in the southern hemisphere, compared to the Coriolis effect in the northern hemisphere, which would produce a clockwise rotation. So as we move into the magma piece, you know, we kind of set the stage from a visual standpoint, from the tectonic standpoint. One of the pieces that we still need to address in this presentation today is what's going on with magma. And in this regard, this is our fluid phase. It's of course represented as it makes its way up and cools and crystallizes to form pillow basalts that are at the top of the ocean crust, and basaltic dikes that fed into those, and of course gabbro below that. So these mafic rocks that are a result of direct melting that has occurred as a result of decompression. So the source rocks that we're looking at here are upper mantle source rocks, and as noted earlier, they are lurzolites. So those are just a type of peridotite that's got a significant amount of olivine and pyroxene in it. So that as these rocks are at normally at a little bit higher pressure, they're also at a higher temperature. And when that pressure gets released a little bit, it allows them to lower the melting temperature because the pressure's been released, and you start that melt. Now, what's interesting in the models that we reviewed literature-wise up to this point is that you get 0.1% melting starting at the bottom of this triangle. And you've got two sides of the triangle, essentially what had been from the late 80s to the early 2000s, as far as how are magmas that are generated under here moving, buoyancy driven, and then more recent models that are really looking at not only an upward movement and a focusing, but truly some sideways movements as well that are occurring with the magma in this setting underneath of mid-ocean ridges as that decompression melting occurs. And again, the structure of the ocean crust, the lithosphere, and the asthenosphere below that. So let's take this most recent model and then transform that into the setting that we were looking at. And that is, so if we take that recent model, we double it over to see where's our melting regime within that, we can see that yellowish and the greenish area where we would have the most melt occurring. And with the current models, this is suggesting somewhere between 10 and 20% melt. So to think about that in a concept that I think is maybe a little more tangible is an aquifer. So if you have water moving through an aquifer, you might have a 10% porosity that water can move through, or maybe a 20% porosity that can move through. So when I think about magma moving through and it being at 10 or 20%, that's how I typically think about that. So as we move from the 2D of a slice down through to a 3D, really we're taking a look at flow that's occurring not only in a buoyancy, but also laterally. And we find, of course, as we've indicated up until this point, that at higher latitudes, we have higher pressures because the gravity is a higher value. And as we get toward the equator, because of that equatorial bulge, we have lower gravity accelerations and therefore lower pressures in those lithostatic load calculations. So then if we take away and look at the inside of this prism now, so we've gone from the 2D to a 3-dimensional prism in which we're considering if we've got magma in there at as much as 20%, how is that going to move? And with the movement from a higher pressure to a lower pressure, what happens to that? Well, it turns out that if this moves according to other fluids on Earth and things that have flow characteristics to them, that will be influenced by the Coriolis effect. And as you can see here, we have a slight deflection to the left, which is going to end up producing a veering of that melt. And as it comes into interaction with the ridge transform boundary together, that it will influence the stress regime, or what's known as the stress tensor, in which you are taking a look at the Z, the X, and the Y directions and how the stresses are being manifested in this particular setting. I think one of the things that we need to consider when we're talking about stresses is that we're really in a tensional setting. So let's take a look at that for a second. With a tensional setting, we can expect that our materials are being pulled apart. And anytime we've got tension in one direction, studies have shown that gives us longitudinal fractures, and in our case, even larger. They're fault sets or kind of swarms of faults that are occurring, and they're in a longitudinal fashion that are perpendicular to the tension that's pulling things apart. But what we see in the mid-ocean ridge systems is it's not just these, but we do have the transform faults as well. And so we can take this simple tension and we can add another planar component to it. So we've got tension in the X direction, and we've got a little tension in the Y direction as well. So if we were talking about a stress tensor, we've got the tension, and then we've actually have compression due to the gravitational and then also the upwelling, so that our strongest forces are sigma 1, if you want to put it in a stress tensor, is going to be down. So it's related to that, directly related to gravity. All right, so let's take then what we know and kind of work through this conceptual model that we have. We're in these tensional stresses. Primary rift develops. So we've got the kind of the reddish orange down the middle is going to be our primary rift, representing that prism that has some magma being generated underneath of it. You'll notice that we've got some orthogonal or fractures that are at 90 degrees to that ridge system. And we find then, if we take and look at flow patterns, that flow would be from higher latitudes at the lower part toward the equator, and that we should have a slight shift to the left as a result of the Coriolis effect. And that's Earth rotating, that's going to have an apparent shift to the left that occurs. Well, our result should be then that this system should rotate counterclockwise. And we find, all right, if we move on to stage 2, we have taken the entire system, rotated it counterclockwise, what was it, maybe 15 degrees or so. And we find that flow continues. So if we use the same logic that we had for the previous slide in this conceptual model, then we find that that flow upwards is still there. It's not quite as strong because we're not directly north-south any longer, but it's still there. It's still roughly to the north. And we get that, again, bending to the left or in a counterclockwise rotation that really pulls on where the two are coming together at a transform fault. It's going to pull on that northwest side, resulting in a movement of the western side slightly to the west-southwest. And now our result should be that we would expect right lateral strike slip fault. So right lateral faults are you stand on one side, you look across, and the material has moved to the right. That defines a right lateral. And so in this case, that's the, when we're looking at the relative motion between these two segments producing this right lateral strike slip faulting. And if we apply that at all locations along there, then we start to see this, which is the ridge becomes segmented. And so our magma components may not be as easily connected. We've got most of that magma is being generated within a segment, and that segment starts to move slightly independently. And so flow becomes more isolated into these segments, and we may even have further rotation in a counterclockwise direction if rotation occurs. So that's really kind of, does the shearing take place at the juncture between the ridge and the transform, or does the entire ridge shift? But both of those could occur and look as though they do occur within our study area. This, we also do note that the minor orthogonal fractures, so ones that weren't so evident right at first, may activate, and they give this kind of stair-step appearance, so that now we begin to approximate what we see in the southern part of the Mid-Atlantic Ridge between 30 degrees south and the equator by looking at this, which is just so incredible to think that, you know, could we be pulling apart the geology, the geologic history, to show what's been happening along this segment of the Mid-Atlantic Ridge? So in summary, we've got bathymetry data and products by GEBCO that we were able to use to find the incredible differences in topography of the ocean floor. Of course, just Ascension Island is the only thing that pops out over the surface. So we've got an incredible amount of topography all below the water surface except Ascension Island. And Ascension Island presents itself a fascinating component, because if we're shifting magma over that direction, that would go right along with why you would have volcanism there. We've shown the lithostatic load calculations and been able to show the graph that Simon showed, was just beautifully done, that showed the slope down and the gravity flow that could enable this magma migration directly related to latitude and then also the depth of the ocean. With the orientation and identification of the structures, those ridge segments, those transform segments, that's really what has allowed us to get to the point of this conceptual model. There's still plenty to do. This is only one 30 degree or 28.5 degree component of the entire mid-ocean ridge system. And there's more complexities within other parts that we didn't have here, but we can begin to evaluate other mid-ocean ridge systems, which we hope to start on this summer as well, and to get into more circle stresses. So there, if you've got an existing fault, what are the stresses needed to reactivate that fault? And that will help us to put some numbers and quantify the stresses that are at work, to be able to indicate those stress fields and show that stress tensor with numbers to back it up. And then, of course, the process that involves submitting for publication, we have had a manuscript out, have gotten review back for that, expect to send an additional manuscript out and keeping up on that, that process. So we'd like to thank you for attending today. And I would like to, a special thank you to Simon and to Adam for all the work that you've done in this. And we're happy to entertain questions.
Thank you very much to all three of the presenters. And usually at this point, you can assume wild applause behind all of those names you're seeing on black screens. Few people knowing how to put the applause hand up. And if people want to show the video for themselves, you can also do that and wave and applaud that way. We do have time for questions, and so I would invite questions to come in. You can, again, unmute yourself and perhaps show your video and ask your question. I'm also going to try to keep an eye on the chat as well, if that is the way that you want to ask your questions. And I'll start with a question while other people are thinking about things. This had to do with something that you said close to the end, Professor Sparks, and I think it was also touched on, I think by Simon or Adam, I'm not sure who, but the idea that this system was a bit simpler than other systems, and I know it was touched on earlier that this was kind of a straight north-south segment. Was that a deliberate decision, which I think it probably was, but it also still sounds very complex. Did you know how simple or complex this was going to be relative to other locations when you started focusing here?
Well, I could answer that, but I think I'm going to let Simon take a crack at it since he had a chance to really take a look at many of the systems around the world. And I'll let Simon start off on that one and then maybe follow up as appropriate.
Yeah, great question, Professor Van Dyke. Yes, that was indeed intentional to look at this 28.5 degree system. One reason being is that there are so many fracture patterns and there are so many additional stresses due to tectonic movement, including some of the pull going on at margins, that we decided to take a closer look at an area where we could clearly see the transform faulting occurring in a way that may be consistent with what we are looking for.
Good. I think that hits it right home in noting that the tectonics elsewhere play on what is occurring. So if there's a nearby subduction zone, for example, if we had looked at the East Pacific Rise, we would have found that the subduction zone of the Nazca Plate underneath of South America exerts a pull, and that pull would need to be taken into account. As you move further up in the Mid-Atlantic ridge, you have a small subduction zone that's in the Caribbean that produces the Lesser Antilles. And so there we would, as we migrate into areas where there are known subduction zones on one side of the ridge or the other, that influences it. And then also the Gackle Ridge, which Simon mentioned, is an extremely slow spreading ridge. And the East Pacific Rise is a very fast spreading ridge. The Mid-Atlantic is in the middle. It's a relatively slow, but it's fairly kind of steady. That was part of the decision as well. Adam, anything you want to add to that?
No, I think you've covered it very well. And I was just going to say it makes it very easy to map when it's all within a smaller range, north and south. But and that's kind of in making a decision. We were originally going to go from equator to 30 degrees south, but focusing even more, the 1.5 degrees to 30 degrees south, there's major transform faulting near the equator. And after that particular region of transforming, there's quite a nice north-south region for us to look at. And that, as Sparks and Simon mentioned, those are able to allow us to see how these major effects of the magma migration might affect the surface or the subsurface features on the bottom of the ocean.
Thank you all for that. We have a question that's coming through in the chat from Victor Norman, who asks, those transform faults look perfectly straight. Are they? And do you expect them to be?
Very good question. The transform margins are generally, we're looking at the macro scale, so we're looking at thousands of kilometers on end. And so we expect them to be very straight, as in and also perpendicular to the ridge margins. However, one thing that we weren't sure about was how consistent that was throughout the Mid-Atlantic Ridge system. And our analysis, as presented in the Rose diagram, showed that our results were very consistent and that the transforms had very similar azimuths.
Yes, and in addition to that, I think when you're looking at these mountains, these are mountain ranges. It's a huge scale, as Simon mentioned, thousands of kilometers north-south, about 1,000 kilometers across in the middle. They are pretty straight, and if you think about the brittle deformation of the oceanic crust, as these fracture patterns start to form, they will start to spread orthogonally, and on large scales, they are very, very straight. But even if you zoom into them and look at them, you can see these features that travel in quite straight lines, and it's quite fascinating actually. If you haven't really looked at the ocean floor, especially at these diverging margins, there's some quite fascinating patterns that we're able to uncover with the bathymetry.
Yeah, I would agree. I mean, we're looking at probably 90 or 95% of them are quite straight in the area that we were in. As you go out to other areas, sometimes they bend. So the way that the shear forces would be working on them, and it's part of the reason that we chose this particular location to start with, is the simplicity of it. And yeah, I think in opening more cans of mid-ocean ridges, we may find that there's definitely some more shearing, and we may get some rotation that shows up in some of those to give either sinstral or dextral rotation as well.
I think that we might have a question coming in from Professor Sterling. Go ahead.
Yeah, I actually had a couple questions and one comment. Going back to Professor Van Dijk's original question about why you chose this area and the simplicity, I thought it was genius too, because you chose the setting where this side of your mid-Atlantic ridge, you have a passive continental margin. And that was alluded to in Simon's discussion, but maybe not picked up by some of the audience. So there you have mirror images on both sides. But I'm kind of arguing with myself. If you go beyond the actual margins of the continents to the opposite sides of those two continents, on the far western margin of South America, you have the Peru-Chile Trench. And if there's significant trench rollback going on there, that's going to be a pull towards the west. And on the other hand, on the opposite side of Africa, you do not have a trench. You have instead the Carlsberg Ridge, which is exerting a push on the eastern flank of Africa. And those are not exactly, neither of those ridges are running exactly north-south, which maybe fits really well into your scheme here. Maybe they're all deflected in the same sense. But at any rate, are there differences in the vectors of plate motion relative to the mid-Atlantic ridge there? So just simple linear dimension of motion. Does it differ from one side of the ridge to the next in the South Atlantic, let's say?
So I think that that's a fantastic question, and one actually we were hoping to answer a little bit as we started into things during interim, to see if we had more of a pull on the west side, and we could pick that up in the topography, but we were not able to do that. Previous studies have looked at the asymmetry of the magnetic signatures. So there is a little asymmetry down there, but not as much in other areas.
Cool. It's kind of like asking whether whether El Nino is related to the North Atlantic oscillation, right? At some level, everything gets connected to everything else. So it's like, because it is a contained system, right? It's a sphere and everything has to take place underneath that sphere. So the next question was a little bit more constrained, but Simon had a graphic where he showed lithostatic loads proceeding away from the equator and modeled as kind of like a teeter-totter with blocks on the top of it. One of the variables, of course, is as you go off, so the variables there were in terms of rho, the density. You have the depth and density of water, the depth and density of the oceanic crust, the depth and density of the upper asthenosphere. And as you model it, the upper crust is 3,200, the asthenosphere is 3,400. But as you know, as you get off axis, the crust itself is contracting. So its density actually increases along a gradient as you work your way off axis. So presumably, maybe sometime in the future, you actually incorporate an extra variable into your multivariable calculus equations that accounts for that changing density. So you have an increase in density in your oceanic lithosphere, and also because you're going off axis, you have an increasing depth of the water column, so you have more weight of water at the farther away you get away from the mid-ocean ridge. And I don't know whether that influences your model to any degree, great degree or not. Maybe it, if anything, it augments it. I just don't know. But I was just wondering what you thought about that.
I think I'll let Simon take that one.
Yeah, that's a great comment, Professor Sterling. But I think, and I think that's very important to consider. I think one thing that is in our literature we found is that most of the magma migration occurs within 100 kilometers from each side of the ridge, down to about 60 kilometers depth. And so we could definitely incorporate that additional variable to that extent to see how it changes the results of our analysis.
Yeah. Interesting. Very interesting. Thanks. I will make one quick note and then I'm going to ask another question. So Simon, I just want to note that on 2 of your graphics, the word lithostatic was replaced by the word lithographic. And there is such a thing as lithographic stone. And I'm guessing it's a spell checker correction or something like that. So you might want to go back and check those.
Thank you. I will.
Yeah. It's something that a lot of people wouldn't catch unless they cared about lithographic stone, which I do. So, and then the last question was this general one. At the start, you mentioned that there are some models of plate tectonics in which they're driven by the forces at the mid-ocean ridge. In other words, it's a push model, and other models in which it's the main driver is the downgoing at the subduction zones. It's a pull model. Do you have any idea which of those 2 models is really the more relevant, or how does that work? Or is it 6 of one, half a dozen of another? Or
that is a very good question, Professor Sterling. And one thing that we've started to explore in this literature, we've found that there's not a crystal clear answer, so to speak. However, we see that that definitely the subduction zones play a very large role in this, and that the divergent margins also play a role. So I think it's a little bit of both. And that a lot of this is occurring on a positive feedback cycle as the magma rises and expels material into the diverging margins, which in addition to the plate movements toward the subduction zones allows for decompression and more magma to be expelled.
Excellent. I see we have several questions in the chat.
Yeah, I'll get off.
Well, thank you for your questions, though.
Nice. It's a genius project. It's a genius project. Yeah.
Excellent. I thought maybe I would just address some of those questions that might be in there in the chat. And so with the ridge segments, we would expect maybe some continual rotation that might help us with how long something has been happening and see if that matches with what's going on in the paleomagnetism and age determination. And then there's a question from Aaron that says, do we find patterns like this on continental masses? And that's a great question as well. They're definitely more complex in a continental setting because of the way that the continental crust accumulates over time and the tectonics that lead to the formation of continental crust. So that hopefully addressed a couple of those there. And then let's see, can you say how the opposite Coriolis effect in the northern hemisphere and the force in the southern hemisphere affect the crust near the equator? That's something we'll have to explore as well. And then do we have other specific mid-ocean ridge systems in mind? I think Simon and I have talked a little bit about the Southwest Indian Ridge being of especially interesting, kind of as a very slow spreading ridge. There's a lot of work that's being done on the East Pacific Rise, so I think I would wait on that and maybe consider some of the others, because there's some really good models that have a lot more going on in them on the East Pacific Rise. So I know we're past time. I don't know if Simon or Adam, if you guys wanted any concluding remarks.
And I'll say just before you do that I'd invite people to stick around, kind of like the post seminar informal chatting afterwards. So we still will have more time for questions after this. We're going to have either Adam or Simon or both give concluding comments if you've got a few in a minute. But I'd also like to invite everybody in the audience to hoot and holler wherever you are right now and give that second round of applause to officially end this seminar. But do stick around if you've got more questions.
Well, thank you, Professor Van Dyke, and thank everyone for listening. I greatly appreciate opportunities like this to speak and do research. And I think we've all really enjoyed this, and it's really asking a lot of questions. I think that's kind of what the big takeaway is, that there's really a lot we still don't know. And there's plenty more research to come out of this. And hopefully we can continue to share the results with you.
Yeah, thank you for taking time to listen. This is definitely, as Adam said, a project which we still have a lot of work to do and many more questions to ask. So continue to ask those questions.
So we have no official other questions coming through in the chat. I'm not sure if Neil, do you have a question? Excellent. Go ahead.
I have a question. Yeah, so as I was watching your presentation, I was really quite struck by how beautiful your data representation was. So I'm kind of wondering, and this is a more technical question, what specific software did you use to create those figures? And then also, yeah, like what were your specific considerations that you had in mind as you're doing that in terms of like filtering? Like, how did you filter your data? Was there any noise that you needed to clear up, or was that kind of something that you didn't need to spend too much time on?
Yeah, so I assume you're talking about the bathymetry, and you're right. It's very fascinating. We, in particular, well, all the processing was done in ArcMap. So ArcGIS, ArcMap, spent time in the lab down in bottom of North Hall, and just downloading the GEBCO data. In terms of filtering, that was something which I thought about doing. The raster, the raw raster that we downloaded, actually was quite useful in detecting a lot of the topography. They've done a lot of interpolation and work on the data set that's publicly available. So there's not too much in terms of looking at the raw data. It's pretty useful. I think what you do with the visualization really makes a big difference. I remember Simon was saying after I had done some of the work over interim with the hill shading and the progressive color shading, adding those the hill shading and the colors to the bathymetry really helped attenuate the topographic relief and the differences. Whereas looking at the raw data, you can't really do that. I think in terms of the GEBCO data set itself, though, it's relatively accessible. If you have access to ArcMap, you can download and start to play with different ways of representing the topography. And you mentioned what software we use for figures. So I think Simon and Dr. Sparks, they were mostly working on those additional figures, but I can speak to the bathymetry, and of course that's all done in ArcGIS.
Yeah, and we also use a lot of Python programming to do some of the statistical analysis for some of the other figures, and we use some other programs also to create the rows diagrams.
Yes, I forgot to mention. So all of the 40 plots of the cross sections, that would be that'd be a ton of work to do in Excel. So all of that was done using Python and Matplotlib. So I exported the cross-sectional data sets and then put them into Python to do the plotting. And I think Simon used Python for the rows diagrams as well.
Yeah, thank you. And then I kind of have like a little unrelated part too that I just thought of. Professor Sparks, I think you mentioned that there's a lot more to be done. There's a lot more tracks in terms of bathymetric data to look at besides the study area that you focused in on this time. So I'm wondering, that kind of begs the question for me, what's the next area that the project is going to focus in on?
I think that's the sky is the limit there. And I think naturally to move northward and start to deal with some of the complexities of the mid-Atlantic ridge, or there are 3 ridges over in the Indian Ocean. So whether or not to take those on, there's a really slow one, a relatively fast one, and then another one that's in there. And of course, with the Himalayan mountains, that's a whole other ball game going on with that and the history within the Indian Ocean. So I think it depends a little bit on as we go into summer research season, where the interests are with my student researchers. So.
Thank you.
Mm-hmm.
While we're waiting for the next question to come up, I'll just invite everybody back next week for more student research presentations. So you can continue to hear some good things that are being done in the department with more of a focus on dune history and dune activity, including getting some plants and some interesting layers into things. So please do think about coming back next week. We've also got a small enough group now that if you want to just pop your video on and give a wave before you leave, feel free to do that as well.
Thanks. It's great.
Nice to see everybody again. I'm still stay at home, stay safe. So I haven't seen you face to face. Maybe next summer.
Thank you.
Thank you.
Bye now.
Thank you.
Yeah, I was very impressed with your graphics all the way through. And I guess I can personally say that you took a difficult topic And there were a few moments where I thought, oh no, I'm never going to get this. Look at all those equations on this slide. And was impressed with all three of you with how you kind of took it apart and guided us through the topic. So thank you for the planning and the preparation, and also the hours of doing graphics that went into this presentation.
Yeah, I think Simon was mentioning earlier today, some of those graphics, they take you a lot longer than you would expect to put them together. But then if they can show the concept visually so that someone else can understand them, or just see the data in that way, is really, really helpful.
Yeah, one other thing I was thinking is I'd love to get one of the maps printed out full size on the wall, so we could look at that in the geo department. That'd be pretty cool.
Okay, consider it done.
Yeah, you can put it in the map library or something. You can make multiple copies so people can check it out and use it in labs and stuff.
Yeah, I think there's probably like 6 or 7 different maps with different data being represented. I wasn't able to show all of them in the presentation, but I've got a lot of cool maps we could print out. That'd be awesome.
It might be fun even to put it like, at an 8 foot, where are you on the ridge? Where's your height on the ridge? Did I make it to Ascension Island or not? No, but
I was really
that's
impressed.
exactly right. Oh, go ahead,
Thank
Neil.
you.
Sorry.
Thank you, Neil. Yeah.
No, I was just saying that I was really impressed as well with the figures.
Yeah, thank you.
And hopefully you'll find more uses for them in the future. But sometimes I also find when you're making figures and you're being challenged to how can I best represent this in a graphic, you learn more about what you're making the figure about too, because you get it kind of half done and then you go, no, that's not right. Like, what really is going on here? So, so hopefully you'll find that those hours of effort have multiple benefits to your team. Professor Sparks, you're muted.
Yeah. Sorry about that. Yeah, I just realized it. To pull in for some of the mathematics behind this, I mean, that's really the next stage, is to be able to put that into play. So I was thinking, oh, we should ask you, when it's the Coriolis effect and you have a certain viscosity, what's the potential for actually moving things? To be able to answer some of those questions. Those are difficult questions that hopefully if we've got the right mix and the interest as we continue this in the future, that we can start addressing some of those. Yeah, thanks so much for hosting this too.
Oh, you're very welcome. Is there a large body of other people working on similar projects in other areas, or are you really like taking some opportunities of data that's available and interests that you have to go in a direction that nobody has really gone in before? Do you have some sense of where you fit into the broader scientific community?
I think Simon might be able to answer that. I mean, I could add to it too, but Simon, I'll let you take it.
Yeah. This particular research has not been performed on a large scale recently. We have a few papers from this general area of interest going back to the 1960s through 1980s. However, there hasn't been a whole lot of work on the macro scale of looking at what's going on alongside an entire diverging margin. However, there has been some additional research going on regarding magma generation below diverging margins, but they've been mostly looking at what's going on in a 2D space. So what's going on laterally from the diverging margins and below the diverging margins. One thing that we're interested about is possibly maybe sparking a new area of research where we're starting to look at what's occurring latitudinally along these margins.
And I imagine if, as you said, the initial interest is the 60s, 70s, and 80s, you've just got a whole host of new visualization tools and and computational mapping tools available to you that the early people asking questions wouldn't have had available. Not to mention perhaps even the database, like the sonar data that you're dealing with. I imagine that's fairly recent and is opening up whole new worlds for your analysis.
That's exactly right. That multi-beam that Adam was mentioning, I mean, some of that is in the recent literature for specific locations. And I think that there's great potential out there right now in general, people that are working in ocean settings, whether it's convergent or divergent margins like we are really looking at this side scan sonar to get details of, do you have faults that you can recognize, slip faces that are showing up in the geomorphology that are structural. So yeah, there's a great potential. And I think that a lot of those concepts were kind of pushed off in the 70s and 80s, saying, I mean, that just doesn't seem possible. How could that be strong enough to do those things? And so the additional database, the additional tools, the level of mapping that we're able to do, hopefully we can exactly spark that right up and open up an incredible area of research for mid-ocean ridges and more.
And then Adam, I need to compliment you on keeping cool under lights going off all around you.
Yeah, it's fun.
Including as you were presenting. So
yeah, I hope I handled it well.
You did, definitely did.
There must be some way to turn that off while it's essential, but I guess I sit too still when I'm presenting. I don't know.
If you couldn't see behind the names because people had their videos off, but any faculty member was just, I mean, we have it going off in meetings and all sorts of things. We know that feeling. So you handled it very gracefully.
Thank you. Yeah.
So, well, I'll officially call us to a close here and end the meeting. Thanks to our 2 remaining audience members who are still with us, and definitely thank you to all of you presenters for the work that went into this beforehand, but also for explaining it, for fielding questions, and for starting our seminar series off on a great foundation for this semester. So thank you all.
Well, thank you.
Yep. Thanks for hosting us.
Okay.
Bye-bye.
Bye to everybody.
Bye.